Thank you.
Where is this lighting? That goes in the distance.
It was a debate as to how much time I should spend on the graphics versus the talk.
Okay.
This is what you get. Sorry. Right. So thank you very much. And by the way, for the microphone, I'm okay just standing here.
Yeah.
Great. Okay. Thanks for the intro and thanks for having me. I actually gave a talk here 7 years ago, almost exactly. You see a few familiar faces. Unfortunately, that coincided with a huge snowstorm. And so most people were stuck at home with kids who could not go to school. I think if we had had Zoom back then, it would have been helpful. But anyway, it's great to be here now. Thank you all for coming. So let me get started. So I'll be talking about galaxies far, far away, and maybe the more informative title is mapping the cosmos. Here it says with the dark energy survey, but really more generally with photometric galaxy surveys, so doing weak lensing and galaxy clustering. So instead of showing you the traditional pie charts, I know this is a pretty sophisticated audience, I'll just do an intro to this talk with 2 XKCD comics that I particularly like. The first, basically, the universe is weird. It's made of weird stuff, which we don't understand. Most of it is dark matter and dark energy, which we cannot see directly. This is exciting if you want to study unknown things, but it's also a pain because it's hard to study something you can't see. The other one is actually just from, I think, last week. I thought it was apt. There are a lot of galaxies out there. So this is sort of our saving grace here. We can't see dark matter or dark energy directly, but we do have a lot of galaxies to work with. And so the name of the game here and what I'll be talking about is how we use millions and in the near future, billions of galaxies in some statistical way to understand the weird stuff that we can't see. Okay. So this should be familiar to most of you, but just mainly to introduce a little bit of terminology in case you haven't seen these parameters before. When we do these sorts of analyses, the things that we are constraining fall typically into the category of geometry. So this is the properties of the homogeneous universe. The expansion rate is a function of time, how luminosities and angles are related to distances. And the growth of structure. So this is how clumpy the universe is. So this is not a property of the homogeneous universe by definition. It's how the universe is departing from homogeneity. And so this is quite an old simulation now. I won't use this because I don't think it works on the screen. This is quite an old simulation, almost 25 years ago, because I think you have to go pretty far back when people are actually putting a lot of computing power into cosmologies that are obviously wrong. But you can see, well, maybe I'm not sure, you can kind of see that the clumpiness looks very different. You have different amounts of dark matter, of dark energy. They evolve differently with time. You can even starting with similar initial conditions end up with very different structure in the late time universe. So in addition to mapping out how the universe is expanding, we want to figure out how structure in the universe is growing statistically. And both of these give us good lever arms to understand what's happening at the fundamental level. I said there'd be a little bit of parameter jargon in case you haven't seen these before. The parameters that we typically quote when we're measuring the growth of structure are either sigma 8, this is density fluctuations on the 8 megaparsec scale, or S8, which is the weak lensing version of this. So this is rescaled by the matter density to capture kind of the actual amplitude that is most directly measured by a lensing experiment. So I'll use these two somewhat interchangeably. S8 is kind of the thing that if you read an abstract of a lensing paper is probably the thing that's being quoted.
There's usually a little h minus 1 there, right? Even though we should now know h very well. H minus 1.
Yeah. That's right. Sorry, there's a little h there. Yeah. Speed. Sorry. Okay. And then, thinking about these axes of geometry and growth is also, I think, an exciting time. This plot is a couple years old now, but I think it captures still fairly well the state of things. Things were weird enough up until a few years ago with just having dark matter and dark energy, which were these mysterious things. What happened, starting around 2015 or so, maybe slightly sooner, was that different observational methods to probe both growth and geometry within the lambda CDM framework started to disagree with each other. So we see here on the x-axis a measure of the Hubble constant. So this is a geometric probe. On the y-axis, this is basically the sigma 8 parameter, so the growth of structure probe. And we see 3 different data sets. So in the red is just a local measurement of Hubble. This is from the Reese results, the local distance ladder with Cepheids and supernovae. The blue is a combination of various low redshift data sets, so sorts of lensing that I'll be talking about today, but also supernovae and baryonic acoustic oscillations. And then the green is the Planck CMB interpreted through the lambda CDM model. And you can see in these two different directions, there's really not a lot of agreement. So the biggest disagreement here is between the local measurement of the Hubble parameter and other ways of measuring expansion. So if you just go in local, measure how fast things are expanding locally, you get something like 73 or 74 for the Hubble constant. If you infer that value using these other data sets, you typically get something more like 67 or 68. And the error bars are now small enough that this is a pretty significant tension statistically. I think you can pretty much rule out the fact that this is just a weird fluctuation. It could be a systematic that we don't know in one or more of these data sets, but I think it's probably unlikely to have just been a statistical fluke.
And are red and the blue, do they overlap in Z?
Do red and blue overlap in Z?
I mean,
Not
says low Z.
Yeah, so right, so low Z meaning not. So this is really local, so very local, very low redshift. Low Z meaning redshift between 0.1 and 0.7, something like that.
So there's no overlap between.
So there's not really any overlap, no. And then low Z as opposed to the CMB, which is high Z. Yeah, that's the relevant distinction. Yeah, yeah, somewhat weird terminology. So right, anyway, I mean, just to wrap this up, I mean, this is I think telling us that, you know, who knows, maybe lambda CDM needs to be amended or something else needs to be added to our model. But I think this makes me optimistic that something exciting will be discovered soon, especially as more data comes in. Yeah.
Tip of the giant branch, where would it would be sort of.
Yeah,
the blue and.
yeah, I think it's somewhere sitting kind of 70, 71, something like that. I don't know actually the latest to the red giant branch thing is, but I think it is sitting somewhere in the middle. So yeah, I mean, it is. You could argue that maybe what's going on is a systematic in the Cepheid approach, but if that's not the case, then there's some tension there. Okay, so my talk, what you know, with that motivation out of the way, I'll spend a little time just for context talking about our recent year 3 cosmology analysis in the dark energy survey. I know that you had Alex M on recently, who probably gave a much better description of this talk than I could, or about that than I could. So I'll just provide a little bit of context there. I'll mention what's coming up next, the Rubin Observatory. But then I hope to get, for the second half, and hopefully a little more than half of my talk, a description of some of the details of how we actually do the necessary astrophysical modeling to do this sort of analysis. So this is where I spend a lot of my time. It's sort of been one of the main roles that my group and I have played in these collaborations. And within that subset, I'll be talking about 2 different approaches that we've been taking. So historically, what I've been doing mostly is nonlinear perturbation theory to describe these galaxy statistics. So I'll say a little bit about that and how we've applied those techniques to the actual data analysis. And then some newer stuff that I've been spending a lot of time in just in the last year or 2, which I'll say something at the end, is giving up basically on doing this analytically and instead using some analytic simulation-based methods to both do the modeling and to produce large realistic mock catalogs that we can use for various purposes. Okay. So again, if you saw Alex's talk, you probably saw a slide somewhat similar to this, but this is just the outline of the basic method here. So unlike a spectroscopic survey where you have a nice 3-dimensional map of your galaxies and you can do like high resolution baryonic acoustic oscillation or redshift space distortion measurements, with the photometric survey, we don't have that 3rd dimension in very, very good resolution. We have, you know, low quality photo Z estimates, which give you some idea of where these galaxies are, but it's noisy. The advantage we have instead is that we have a lot more galaxies because you don't need a spectrum for everything. You just need an image. So you can go a lot fainter and a lot deeper. And the other advantage is we have shapes. We have the shapes of, you know, as I said, millions of galaxies. And so we can take an observation. This is an example image from the dark energy survey. And we can use this galaxy information, so their positions and their shapes, to directly make a map. So you see here, in this bottom map, this is just directly taking the galaxy positions, smoothing them on some scale. This is a somewhat old plot. This is, I think, 1300 square degrees of the sky from the earlier dark energy survey analysis to give you some sense of scale. But you can smooth the galaxy positions and make a map of the density field as traced by the galaxies, or you can use the galaxy shapes and the fact that we know that the shapes are impacted by intervening matter. This is the gravitational lensing effect. And you do a statistical analysis of correlations in their shapes. And this tells you, again, in a statistical sense, how much mass is there between you and these background galaxies. So that lets you construct a different map of cosmic structure. So we call this the lensing shear or the convergence map. So once we have these, we have two different maps. You can do the statistics on them individually, or what's really become the state of the art, what everyone's doing now with these sorts of analyses is you analyze them jointly. So you have the autocorrelation of galaxies, this is galaxy clustering. You have the autocorrelation of the lensing, this is sometimes called cosmic shear. And then you have the cross correlation of the two, this is galaxy-galaxy lensing. So if you're doing this with 2-point statistics, which is still what is sort of the workhorse of these analyses, even though it would be great to go beyond 2-point statistics. And I guess I'll talk maybe a little bit about that at coffee tomorrow, some work that I'm pushing on to try to look at stuff beyond 2-point statistics. But 2-point statistics really are still the bulk of the results that we're doing. You have 3 different possibilities if you have these two maps. So we call this, we got kind of cut off at the bottom, but we call this a 3x2 analysis. This is jargon, it's stuck. We'll live with it. It's not the most descriptive in the world, but it gets the point across. 3 different possible 2-point statistics that you can measure. And this method has the advantage of, well, it's statistically sort of optimally combines all your information because you're properly combining this with the full covariance between these different measurements. Each of these maps individually is subject to a different set of observational and sometimes astrophysical systematics. So if you cross-correlate the two, you can go a long way to reducing the potential impact of these systematics. And then of course, there's cosmological degeneracies that you can get around by combining these maps. So, you know, the classic example is if I just measure galaxy clustering, at least in linear theory, the amplitude of galaxy clustering is this combination of the galaxy bias, I'll talk about that in a second, and this amplitude parameter sigma 8. So if you just measure that, you really don't know which is which. On the other hand, if I measure galaxy-galaxy lensing, there's a different dependence on bias and sigma 8. So by combining these two, I can solve simultaneously for both of these things. And then, of course, if I want to do the full optimal analysis, I also combine with the lensing, which just depends on sigma 8. It has this, you know, a whole separate set of challenges and systematic problems. So really, you can do the best job possible by combining these 3. And I won't say much more about this today, but of course, the ultimate goal with these sorts of efforts is to combine even more stuff. And so this is already something we've been doing in DES with our friends in SBT and ACT and Planck collaborations, where you take an additional map of structure, in this case coming from CMB lensing, and now you have 3 more 2-point correlation functions that you can add to your analysis. And so if you have everything together, then this would be a 6x2 analysis. And the principle, of course, is something that even stops you there. You could add galaxy clusters or some other tracer of cosmic structure and keep going. Of course, at some point it gets very challenging, but you know, this is, I think, the direction that the field is headed in, is have more maps and do a better job sort of mitigating these systematics that impact each map individually. Yeah.
Can you just say 2 sentences about how people make a map of CMB lensing?
Yeah, so this is not exactly my field, but I'll try. I mean, basically, if you have a similar effect of weak lensing on the light coming from the CMB, and this moves coherently the hot and cold spots around in a way that you can model with you know, basic analytically. The nice thing about this is the CMB fluctuations are very linear, so the map is pretty easy. And so you basically apply a filter to your hot and cold spots and lets you reconstruct what the shifts must have been, and that gives you a map like this. But yeah, it's the same general idea. Instead of looking at the statistics of the shapes, you're looking at the statistics of the hot and cold spots. And there's a predictable shift that you get. Okay, so yeah, again, just for context, if you have not heard of the dark energy survey, this is sort of a 1-slide stats of it. So this is now a completed observational project that finished a few years ago taking data. We're still analyzing the data. So what came out last year was actually just roughly half of the data set, a little more than half, I think, by number of exposures, but roughly half in terms of, you know, calendar time. So that was the year 3 data set. What we now have is a 6-year data set. That is, as I said, in the process of being analyzed. I hope that will be done early next year, but don't hold me to that. So the DES survey covered about 1/8 of the sky. It's in the southern hemisphere, it's in Chile. And as I said, we're now in the regime of hundreds of millions of galaxies. So the year 3 cosmology analysis had 100 million galaxies that were detected with high enough signal to noise to have usable weak lensing shapes. I think there was a total of 300 million galaxies in the sample, about 2/3 of which were not usable for the lensing analysis. But this is, for a sense of scope, this is a lot of galaxies that we're analyzing.
How do you define usable and non-usable?
I'm the wrong person to ask that question. There's some signal to noise threshold and some other quality criteria where you say the shape that you would measure on this galaxy is just not reliable. So I don't know, somewhere around signal to noise of 5. I don't know the exact number, but there's some cutoff where you say, this is not well enough measured.
And you want them to have certain well-determined electricity? Or
That's right. So there's a raw signal to noise threshold, and then so the way we measure the shapes is something called meta-calibration. That's the main method, and this has some internal quality checks of, is it properly fit by a Gaussian mixture model, or is it too noisy to fit this model, in which case it hits a flag and gets thrown away. And then there's also redshift cuts. I mean, there's a very long high redshift tail of these galaxies, and you just sort of cut at some point and say we don't want to deal with everything beyond some redshift. But I think mostly they've been thrown out just because they're not high enough signal to noise. Because of the luminosity function of galaxies, you're typically always dominated by the faintest thing that you think you can resolve. So there's always more galaxies as you go fainter. That probably explains this ratio of 2 to 1. Okay. So this was us pre-COVID, shortly before year 1 cosmology analysis came out. Everyone is together and happy. This was us last year, shortly before year 3 cosmology analysis came out. We're still putting on a brave face, but as you can imagine, it was tough to put the final push out on an analysis like this when you're in your living room. But we got it done. Yeah, this is fortunately, I think this is not fully representative of the number of people. This is like who could be bothered to send in a picture, which is probably actually a decent proxy for the people who were doing a lot of the work. Sorry, this is on YouTube, huh? So anyway, apologies. As I said, I'm not going to get into the technical details of the analysis. If you saw Alex's talk, I'm sure she did a great job, but there's also a webinar on YouTube that we put out when the results came out. So if you're interested in a lot of the details of how the data was cleaned and collected and various steps of the analysis, I would suggest you check this out. Okay, so we measured these 3 different 2-point correlation functions. We have the galaxy-galaxy lensing here. We have the cosmic shear, the plus and the cross components of the cosmic shear, and we have the galaxy clustering in the bottom. So I'm not going to try to describe each of these panels. Just to say, there's a lot of data points that we measured that we're trying to fit with a single model. This is, I believe, the best fit lambda CDM model that you see in the black curves. The other point I want to make, which will be relevant for the second half of my talk, is that to do this analysis, we threw away a lot of information. Everything in gray, this is the, going to larger scales on the right, smaller scales on the left. Everything in gray is on smaller scales, where for one reason or another, we didn't think that the model that we had available was good enough to describe the data in a robust way. So we basically just threw away those data points. There's a ton of signal to noise that was measured, this beautiful data set that we couldn't use. And so obviously it's unrealistic. I think we would be able to go all the way to the left and include all these data points. But even small improvements, being able to push a little bit to smaller scales, will bring with it a lot of new signal to noise, which could potentially improve constraints without needing to build a bigger, more expensive telescope.
What are the panels, the redshift beams, or why are there many?
Yeah, exactly. These are, so we have, you can't really see the numbers, but you have well, actually 6 redshift bins in the lens sample, and then you have 4 redshift bins in the lensing source sample. So it's just the various cross correlations. So we analyze this with a model with 7 cosmological parameters and 20 additional parameters that describes various astrophysical and observational systematics. So we're jointly trying to explore a 27-dimensional parameter space. That's what determines that curve that we showed. I prefer to think about this in a somewhat simplified way, a more kind of theory-oriented view of our model. So we're trying to describe 3 different statistics. So this is now in terms of the power spectrum, so the 2-point Fourier space function. We have the cosmic shear, we have E modes and B modes. The E modes are driven by the lensing signal, and then these 2 different GI and I terms. This is the intrinsic alignments, which I'll talk about in a second. The B modes are coming just from intrinsic alignments, so that's the second line here. We then have the cross correlation between galaxies and lensing. So this is the galaxy-galaxy lensing model. This has, for our fiducial model, just a linear galaxy bias, a lens magnification term, a matter power spectrum that we're getting from HaloFit. And then we have intrinsic alignment contribution. We have something we call the point mass. This is basically accounting for mismodeling on very small scales. Since lensing is a non-local measure of the mass distribution, you actually need, in principle, an accurate description of your mass all the way down to the smallest separations. Since we don't have that, we basically account for some excess or missing mass, which we call the point mass. So maybe a somewhat technical point, but it's needed to go at this level of statistical precision. And then finally, something I'll talk about again in a bit is another branch of the analysis where we don't just use linear galaxy bias, but we go to nonlinear galaxy bias. And the hope here is that even though you're introducing additional astrophysical parameters, you're able to then go to smaller scales, include the smaller, the higher sample noise data points at those small scales, and come out on net with better constraints. And indeed, we show that it takes some work, but you do a bit better. And then finally, the galaxy clustering is this bottom line, and we have again a linear galaxy bias, and in the case of this other branch of the analysis, nonlinear galaxy bias terms. Okay, this was The Guardian. I think a very misleading headline on the day that our results came out, but it may be attention grabbing, which is, I guess, good if people click on it. So was Einstein wrong? As always, when there's questions like this in a headline, the answer is no. I would say the main headline result when we take a step back and look at what we showed with this year 3 analysis was that lambda CDM and GR do pretty well. I talked about these tensions at the beginning that are sort of motivating a lot of this work. And we can see here on the right, if you compare our best results in gray with the CMB constraints in green, there is still some perhaps tension, and I'll quantify that in a second, but it certainly hasn't gotten bigger, even though our constraints have gotten tighter. So it's still possible there's a tension there, but we can't say anything definitive about it. And we also see nice consistency between, if you just look at the lensing in blue, the cosmic shear, and the clustering in galaxy lensing in orange, and you interpret these both within lambda CDM, they lie pretty nicely on top of each other. So again, no glaring evidence from any of this that lambda CDM is wrong or that GR needs to be modified. Headlines to the contrary. So looking at just the dark energy survey results themselves, we, as you would hope, have more constraining power than we did in our year 1 analysis. This is about what we would expect, a factor of 2 improvement given the extra data that we have. Again, you see the improvements you get by combining these data sets. So blue is just lensing, orange is the galaxy lensing and clustering, and you do a lot better by combining them. If we compare to the CMB, so in year 1, we had quoted about a 2.2 sigma tension between the CMB and our combined constraints in this S8 parameter. So now this is down to about 1.5 sigma, even though the constraints are tighter. So again, it's not like suddenly the tension is completely gone, but we're not saying that we have any strong evidence that it's getting any worse. So I think this is still sort of to be determined.
Yeah, but you're not showing H, so you don't have much information about H.
So here, okay. You beat me by 1 second. So we also, alone, DES is not able to say much about H, but combined with other data sets, we are. So this is sort of our latest contribution to the Hubble tension debate. So if you just look at the DES results and combine it with BAO constraints and BBN constraints on baryon density, so no CMB, you get the black-gray contour. So still sitting nicely at this lower value that's consistent with the CMB, which is in green. You can combine, if you like, with the CMB, and then you get this really tight blue constraint, which is very much still not consistent with the local H measurement from shoes. So the tension hasn't grown, but it also hasn't shrunk. So this seems to be sitting at about the same place as before. So one mystery you may have heard about if you were following this analysis, or maybe Alex talked about it in her talk, is something called the X factor. I'm not going to say a lot about it now, other than I think for transparency, it's good to point out when something goes wrong in an analysis. So we tried to do everything blind. We made all of our analysis choices, how we were going to model it, what we were going to show, before we actually knew what the results were. And we did, I think, a great job of that. But after we unblinded, we actually saw something that looked like this plot here on the left, where if you look at the cosmology constraints from one particular lensing sample, something called the red magic sample, if you look at combining galaxy clustering and galaxy-galaxy lensing, you get a very different result from if you combine with the cosmic shear. So one way to interpret this would be an anomalously low cross-correlation coefficient between the galaxies and the matter density. So typically when you're modeling something with linear bias, the assumption is that the cross-correlation coefficient is 1, so that these fields are correlated with each other completely. And once you start adding nonlinear biasing corrections, that will naturally lower this cross-correlation coefficient, but this is something that is appearing on very large scale. We wouldn't expect this to be an issue, but instead was coming in at sort of the 10 or 15% level and lowering this constraint. If you look at this in the full 3x2 analysis, in fact, adding the cosmic shear kind of calibrates this effect away. And so if you see, let's see, which curve is it? This would be the big dashed line up here. It sits very nicely at the more accepted cosmology results. So basically by adding the cosmic shear, you're calibrating out this effect, and it's solving for the red galaxy bias. But this is not true anymore once you look in an expanded parameter space. So on the right, if we're trying to constrain dark energy, so instead of looking in a lambda CDM model, we allow the equation of state to vary. In this case, this extra freedom, or whatever this effect is that's causing this decorrelation, seems to actually look like a highly non-cosmological constant dark energy. So this upper big dash line is the relevant contour here. And so clearly there is an issue, we think, with the data. So this is still somewhat unsolved as a question. Our best guess right now is that there was an observational systematic which was not accounted for because we didn't know about it, and we didn't see it in any of our checks. That was essentially giving small variations in color correction as you look across the footprint of the survey. And this red magic sample is a very particular color selected sample of galaxy. So if there's some coherent change in how colors are determined across the sky, this is going to look like some structure in the galaxy density that has some power on these large scales. So this is our best guess for what was going on, but this is still not 100%. So yeah.
So can you sort of try to tackle this by kind of starting from the red magic sample and then expanding the...
That is exactly how this has been answered. So basically you take the red magic sample, you make it a less restrictive color selection,
and then move,
and it seems like this mostly goes away.
I see, interesting.
Yeah, but that's a great idea. That's exactly how to get at it. Yeah.
Yeah, so sorry, could you clarify here the contrast, what they are, the orange, blue?
Yeah, so on the left, so this is all in lambda CDM. So, right, so I'm kind of glossing over this quickly, so I apologize. The fiducial sample is using a totally different lens sample, which doesn't have this problem. So we trust the results more. So that's sort of the baseline you should be comparing to. So that's the solid gray and the solid black lines. The other lines are all using this other lens sample, which we thought was going to be our best lens sample before we unblinded, which is why I think it's as important to be transparent, as we kind of switched what we were saying was our fiducial sample after unblinding. This is different variations of that analysis. The blue is just cosmic shear. The orange is galaxy clustering with galaxy-galaxy lensing. And it's really this shift between the two that's the indication that something is wrong. You would expect these to lie on top of each other.
Then you change the sample and you get the other one.
Exactly. Or in the case of lambda CDM, if you combine the two, the data actually then prefer the higher value of SA. So that's kind of the self-calibration that happens, but that really only works in lambda CDM. And I think, you shouldn't it's good that it works, but I think you also can't put too much faith that it will always work, because as you see, it doesn't work in WCDM. There's no way a priori to know what's going to happen.
So the only sample you had is red magic.
So there's red magic. The other sample is called maglim. That's the
Yeah,
future sample.
but is that because you had fewer galaxies here? I mean, the contours are bigger, right?
So it's very similar. I mean, so if you look at the solid versus the dashed, there's a slight shift, but the contours are basically the same
No, I mean,
size.
the colored versus the black one. So
This is because these are not combined. This is just galaxy lensing and galaxy clustering. This is just cosmic shear, and the other ones are when you combine all those together. So that's really where the statistical power is getting better. But the two samples have very similar total constraining power, as you can see by the fact that the solid and dashed lines are basically the same. Yeah. Any other questions about this? So before we move on to the next part of my talk, just let me very quickly summarize. I think these results were very exciting. It was a lot of work by a lot of people, and it was a pleasure to be part of it. It certainly gave us something to do during lockdown. I think, as I said, the headline result, lambda CDM and GR are still, I think, in pretty good shape. This S8 tension is remaining, but perhaps slightly reduced. Certainly has not grown with these results. The Hubble tension remains. We have this mysterious X factor, which we're starting to get a handle on, but is still under investigation. And then two other points, which I'll come back to now in the second half, which I'm particularly excited about, is that we showed in this year 3 analysis that you really can increase your constraining power by using a nonlinear galaxy bias model. And the thing that I actually spent most of my time on was improving the modeling for the intrinsic alignments. And so this was the most sophisticated modeling for this intrinsic alignment effect that's ever been applied in the galaxy survey. So, just before I move on to that half, just a quick teaser of what's coming up. So as I said, DES is done taking data. We're doing the final analyses sort of in the next year. And the next big thing for this sort of analysis is going to be the Rubin Observatory. So this was formerly the Large Synoptic Survey Telescope, LSST. That acronym has been maintained as the legacy survey of space and time at the Vera Rubin Observatory. It's a huge pain to write out in a proposal, but I think it's a good name change. It's a huge camera, 3.2 gigapixel camera on a very big telescope. So really both the camera size and the telescope size are large upgrades over the dark energy survey. This is going to map out really the full southern sky, so about half the sky, somewhere between 20 and 25,000 square degrees, depending on the final survey strategy. And it's going to do this at a really high cadence. So really almost the entire southern sky every 3 days or so. And over 10 years, just building up a really deep data set. We expect by the end of this 10-year survey, have about 20 billion galaxies. So almost a 2 order of magnitude increase from what the dark energy survey has done. And as you can imagine, there's a ton of great astrophysics you can do with this sort of data set. So the dark energy side of things, we have the Dark Energy Science Collaboration. It's just 1 of 8 science collaborations that's planning now to use this for their favorite science case. So anyway, I think I'm sort of pivoting towards spending a lot of my time working on this. I have already been doing that for a while. I'm very excited about it. Okay, so second half of my talk, and I think I'm doing pretty well this time. So as you can imagine, actually doing this analysis is a ton of details. And the thing that I've been working mostly on is providing modeling that connects the underlying dark matter structure, which is the thing for which you have good modeling, from a simulation or from your favorite Boltzmann code, and the actual things we can observe. So the galaxy observables. And I'll say a little bit about 2 different approaches we've been taking. So nonlinear perturbation theory, and then more recently some simulation-based approaches, which I think are very promising. Okay, so this is the problem, as I just said. This is what your simulation gives you, or if you have a nice emulator or fitting formula for the dark matter power spectrum or some other dark matter statistic. If I give you a set of cosmological parameters, you can give me the statistics of dark matter without too much trouble. This is not to say it's an easy problem. Lots of people have done great work to do this, but this is sort of where I think we're pretty theoretically solid. What's much harder is making the connection between where the dark matter is and where the galaxies are. But of course, that's necessary because all we can see is the galaxy. So to illustrate this point, this is a hydro simulation. It's somewhat old now, but I think it's a really nice visualization of what's going on. And we have in purple and white the dark matter filamentary structure. So we see the voids and the clusters and the filaments. And in these overdense regions is where galaxies form. So this was a hydrosim. So if galaxies actually were forming in the simulation from initial conditions of gas particles. And you can see each red line is the position of where a galaxy formed. And the orientation of the line is telling you the orientation of the galaxy. And the length of the line,
Speed vector?
actually just ellipticity vector. So not the spin, just if you look at the principal axis of the galaxy projected on.
This would be all spirals or?
This is everything. This is anything above some mass threshold. I don't know what that threshold is, but yeah, any galaxy that was resolved above some mass threshold. And they just look at the principal axis, major axis. Right, so the orientation is telling you the direction of that axis, and the length is telling you how elongated it is in that direction. So this is very exaggerated. This is not actually the size of the galaxies. The lines have been stretched out so you can see it by eye. But of course, the two main things to take away from this is that galaxies do not form uniformly. They typically are only happening in the densest regions of dark matter density. So very special locations. And maybe you can't see this by, maybe you can. I guess it depends on how good you are at doing correlation functions in your head. But there is actually a correlation between these ellipticities and orientations of galaxies and the surrounding structure. So the shapes are also not random. The positions are not random, and the shapes are not random if you look at that in context of the dark matter density. And of course, since we're using positions and shapes to do the inference of the dark matter structure, we need to understand this relationship pretty well. So there we are. Okay, so for positions, this is typically what we call galaxy bias. There are several people in the audience more expert on this than I am, but the general idea here is that the galaxy density and the matter density are not the same thing. So I can make these maps of where the galaxies are, but that is not directly telling me what the dark matter is doing. So you need to know what the relationship is between the galaxy density and the dark matter density. In principle, this is a very complicated problem. The galaxy density could depend on any complicated function of the matter density, the matter tidal field. These things evaluated at different times throughout the evolution of these galaxies. So you can show that there's a linear theory. As always, you can imagine sort of Taylor expanding this relationship, and there's a linear theory expression that's just giving us the leading order contribution. This is called linear galaxy bias, where you just have the galaxy density is some number times the dark matter density. And this works well enough on large scales, but of course, as you go to smaller scales where nonlinearities are important, this will break down. So intrinsic alignments is this question of galaxy shapes. So this is maybe a somewhat more subtle point. So I'll just take a slide and explain what's going on here. When you do a lensing measurement, if you look up in a textbook how you do a lensing measurement, what you're told is that you observe some galaxy shape, and that thing you're observing is some combination of just a random noise component, this epsilon n. You have a spiral galaxy and it's doing something and it has some random shape on the sky. And then on top of that random shape, you put a little small lensing perturbation. So in the weak lensing regime, sort of a 1% contribution to the observed shape is coming from the lensing piece. And so then if you do averaging over lots and lots of galaxies, the random noise component should go away. And what you're left with as your signal is just the correlations of the lensing contribution. And of course, the lensing contribution is coming from the mass that's in between you and the galaxy. So these lensing correlations are telling you about the mass correlations. And that's how you go about calculating directly something like this mass map or the power spectrum of the mass density. So what complicates this is the fact that, as I said, there is in fact a correlation between the galaxy shapes and the dark matter structure. We call these intrinsic alignments. And what this means is that you have, in addition to your random noise component, a coherent, non-random intrinsic component to your shape. So now when I do my averaging, instead of just having the lensing correlation, I have these additional terms, we call them GI and II, that are coming from these intrinsic alignment correlations. So you may remember when I showed the power spectrum model for our analysis, there were these terms that had GI and II subscripts, and this is where they're coming from. And just to give you some sense of the potential scale of this problem, so this was a forecast that we did several years ago for kind of stage 4 lensing surveys, so Rubin or Euclid or the Roman Space Telescope coming up. And now this is kind of extreme, but the idea here is if you were just to completely ignore the contamination from these intrinsic shapes, and if the amplitude of this effect was roughly what we expected it to be, given our best understanding at the time, which hasn't changed too much in the intervening years, you see that there's quite a large contamination from this effect. So once you're at this level of statistical precision that you can get from this, it used to be future surveys, now it's basically the surveys that are starting now, we're talking about really a large contamination. I mean, this would be, if this were true, this would be quite a dramatic result, right? If the equation of state of dark energy was minus 1.5, that would be, well, it would be perplexing, but it would also be quite a result. But of course, in this case, all it is you're taking an incomplete model and interpreting your data with that, and you're getting nonsense. So this is just telling us that it's very important to account for these and to account for them as accurately as possible. Right, so how do we do this? Well, the old method until not that long ago was just to use linear theory. So in the case of galaxy biasing, there was just linear galaxy bias. You have one parameter, maybe one parameter per redshift bin or per galaxy sample that tells you the relationship between the galaxy density and the dark matter. And similarly, you can show that for the intrinsic alignments, there's an analog to linear biasing, a linear intrinsic alignment model, where now the intrinsic galaxy shape is just linearly proportional to the tidal field. Yeah.
So I'm always perplexed by this. So for every galaxy subsample, the bias is slightly different. So there's an underlying, and you have such a large column sort of galaxies of all different types. So there's an underlying distribution of biases. And it's not obvious to me that you can mock it up with one fitting parameter in a sort of unbiased manner. Is it obvious?
No. That's a very good question. So yeah, so there's two, right. So you can imagine that, you're binning your galaxies in different redshift bins, and the underlying galaxy bias or intrinsic alignment parameter is something that's evolving smoothly across that bin. So you could imagine either just saying, I'm going to model that full evolution across the bin. And in fact, that is what we do with the intrinsic alignments. Sort of for historical reasons, that's the way that we've been implementing this model. For galaxy bias, what typically you do is you just pick a number. You say this is sort of the effective bias in that bin. One of the things we do as part of these robustness tests is saying, well, if we put in some evolution across the bin and we assume it can just be given by a single number, how much are we biasing our results? And we confirm that it's small.
Okay.
But you're absolutely right. That is something you should be concerned about and should be checked. And I mean, so I think historically, the reason why we haven't had a smooth evolution for galaxy bias is that we often have, as you go to different redshift bins, kind of sharp cuts in the selection criteria. So in fact, you don't have smooth evolution. You have these sort of step functions. And so it ends up being a better approximation to have a step function model instead of a smooth model. But even within those steps, you could worry about evolution across the thing. Yeah.
In addition to redshift evolution, do you expect any dependence with like mass or galaxy type?
Yeah, absolutely.
Taken into account?
Right. So this is a great question. Not in our modeling. So the hope that we have is that, at least for the lensing sample, it's smooth enough that everything can be subsumed into redshift evolution. So there's could be some intrinsic redshift evolution, but also your sample, the luminosity, the color, the makeup of centrals and satellites is evolving across the redshift. And as long as all of these things are smooth, you can hope that they all can kind of be combined into a single redshift function. That's just telling you about the total evolution of these things. Now, of course, maybe that assumption breaks down, or maybe it's not monotonic and it turns over at some point. But no, I mean, that's another thing that we have to validate. And one of the reasons, in fact, that I've been getting into the simulation stuff, which we'll talk about at the end, is we're trying to test some of those assumptions.
So this SIG, is this the tidal field measured in dark matter?
Yeah. So, right. So first of all, I didn't say anything about the subscripts. This is just because, so galaxy density is a scalar. The shape is a traceless symmetric tensor. So you need these indices. That's just indicating that. The S is, the normalized traceless part of the tidal field from the dark matter.
Why the relation, why the coefficient is not a tensor? Why is it a scalar?
So you're saying why would there be a? I mean, I think the idea here is that there's a uniform response to the different axes of the tidal field.
But I mean, can't you check that in simulations?
Can you check that in simulations?
What do you mean by it? The rotational symmetry? How can this be? Yeah, I mean the indices have to match up.
Yeah, I think all the tensor work is.
So why would one direction in the universe have a different response than another? One Fourier mode going like this have a different response than Fourier mode going like that.
Well, I'm just thinking about, the tensor or the tidal distortion. I mean, why would it have anything to do with it? I mean, why would is this for individual galaxies, or is this sort of averaged over?
Well, right. So this is the nice thing I would say. It's basically an effective model, average smoothing on some.
If it's averaged, yeah, I can believe that. It could be, for each individual model. I see no reason why it would be.
Yeah, I mean, these parameters. So maybe actually I'll just skip to that.
Yeah, this is large scale.
Okay.
Yeah.
Fourier transform as you go k to 0.
So this is a really good question. Let me skip to this bit. So when we're doing these sort of perturbative expansions, what we really are thinking about is you're smoothing on some large scale. You're not actually trying to describe individual galaxies. You're saying, okay, this is a perturbation theory, it's going to break down. So you implicitly or explicitly put in some smoothing scale and say, I'm going to describe these statistics smooth on that scale. And then what these numbers are, once I've done that, what these numbers are is sort of the effective average response of this averaged field to the average underlying tidal field or density field. And those numbers are sort of capturing all the physics happening on smaller scales. If you had a fully generative model for a galaxy formation or a great hydrosim that you really trusted, you could just read off what these parameters are. But if you don't have that, which we don't, then these just become free parameters that you constrain from your data. And they're kind of capturing all that small scale physics that you can reliably model. Yeah.
Another question actually about these intrinsic alignments.
Yeah.
So you had an earlier formula where you said the total expression about what you get for the shear. But so there is one term that's the intrinsic alignment of one galaxy with that of another, and then there is another term. Yes, this gamma G gamma I.
Yeah.
That's the lensing of one galaxy with intrinsic alignment of another.
Yeah.
But so the last one, two intrinsic alignments, can be eliminated if you have accurate redshifts.
Yes, that's right. If you have accurate redshifts, the II term can be largely eliminated.
Okay.
And I think so. First of all, that would require having good redshifts, which you don't have, and also would require throwing away a lot of pairs of galaxies, which you don't want to do. But it's possible. This term is much more pernicious, this GI term.
Yes.
Because then this in principle is any time you have any separation between different lens samples, you're going to have a term like this. So this was, I think, at least in our field, a pretty famous Chris Harada paper that pointed out that this term was really the problem. I think Chris is coming here soon. That's great. Chris is fantastic. But yeah, so Chris wrote a paper, I think 2004, saying this is actually not the term you need to worry about because, as you say, you can get rid of it if you really want to. But there's no way to get rid of that one. It's always there.
So do you know now which of these two terms is most important for you? And
so it really depends on the regime. So we just jointly model everything. It's basically, this is the term at low redshift that impacts things the most. So if you look at just your low redshift bins, the II term is dominating. If you look at anything else, it's the GI term that seems to be the most problematic. But we're analyzing everything together and we're trying to model everything together. So I typically don't divide it up into the two contributions. Yeah. All right, so I want to skip to the simulation bit just so I kind of talk about this. I'll just quickly say, so, the bias experts will recognize this top equation. You basically do this perturbative expansion for galaxy biasing. And we did something very similar for the galaxy intrinsic alignments. This is something that we call the TAP model, standing for tidal alignment and tidal torquing. These are sort of the two astrophysical mechanisms that people have said can contribute to these galaxy intrinsic alignments. And this model can capture both of those, in addition to any other physics that might be relevant on these small scales that can be absorbed into these effective large scale coefficients. So this is the model that we actually used for the Y3 analysis. I was looking actually the talk I gave 7 years ago here, and I had an equation look kind of like this bottom one, saying this is what I'm working on now. And I'm happy to report that we finished it and we implemented it and we put it into the dark energy survey analysis. So let me quickly jump to the simulations. And I'm happy to talk about other stuff, implementing those models and the details of all that. But for the last couple of years, I've spent less time on developing the perturbation theory and a little more time not thinking about how to do this in a semi-analytic approach. And so the basic idea here is you have some large gravity-only simulation where you have dark matter information, you have halo information, but you don't have any galaxies. And then you need some model for putting in the galaxy. So the traditional thing I'm sure you've all heard about is various HOD or sham approaches, which tell you for a given set of dark matter properties, where do you put the galaxies for some desired target galaxy sample. And so what we're trying to add to that is a description, not just for where the galaxies go, but also what their shapes are and what their orientations should be. So to capture both the galaxy biasing effect and this galaxy intrinsic alignment effect. So sort of in parallel, essentially separate work, but using very similar ideas. I've involved with two different methods. The first one led by Kai Hoffman is really designed to produce high fidelity mock catalogs. So this has been used on the MICE catalog for the dark energy survey and the Euclid flagship simulation to try to make mock catalogs for Euclid. This is, as I said, it's really designed for high fidelity properties, so it's kind of slow, which means it's not a good tool if you actually want to generate many different models. But it's good if you want to have a couple really good simulated galaxy catalogs. Method two, which is where I've been more involved lately, is something being led by my graduate student, Nick Van Alphen. And this is a faster, somewhat lower fidelity, but as I said, much more streamlined and fast approach to put in these galaxy properties in a way that you could actually imagine using it to generate a model on the fly. So to give you some sense, and I'll say a little more about this in a second, but we can generate a new galaxy catalog of roughly 100,000 galaxies with these properties in somewhere between a few seconds and 20 seconds, depending on exactly what we're changing from run to run. And that's actually fast enough to put in an MCMC chain. We haven't optimized it yet. We could try to go faster. I think eventually we could also try to emulate this. So this is the sort of thing where we really could, instead of relying on perturbation theory, generate models for these galaxy statistics directly from a semi-analytic simulation approach. So how does this work? So if you look, sort of the old position only HOD or sham, you have some set of dark matter halos, and you want to figure out where do you put the galaxies. So you have some set of criteria for how many centrals and how many satellites do you put in a halo of a given mass. If you have subhalos, then you can do something called subhalo abundance matching, where you essentially just go down your list of galaxies that you want to put in and your list of subhalos that you have, and you populate, most luminous to most massive, maybe with some scatter or some dependence on other properties. But basically, some hybrid of these two approaches is what we're using, where you're putting these galaxies in based on just information that is accessible from a gravity-only dark matter simulation. And what we're trying to do is to expand it from the position only to having information about the ellipticity. So you have shapes and orientations and halos that are not assumed to be spherically symmetric. So the main project, this is on the upper right, this is Nick, who's been leading this work, something called Halo Tools IA. Some of you may be familiar with Halo Tools. This is a public code that Andrew Heron and others have developed. And we're trying to basically create a new branch of Halo Tools that lets us put in this sort of intrinsic alignment information. And so the basic idea at a cartoon level is you're putting in central and satellite galaxies. You are sampling some misalignment angle theta that is itself given by some parameter. So that you set some parameter for every galaxy. This parameter could be a function of the galaxy mass or color or type or its distance from the center of its halo. And that determines a distribution that you draw from. So you could have a distribution that's very peaked at 0, so exactly aligned with some axis. It can be very peaked at 90 degrees, so exactly perpendicularly aligned to that axis, or it could be anywhere in the middle. And you draw a random number that tells you where it should be sitting within that distribution. And then that tells you, once you put the galaxy down, which way it should be oriented. And again, with Halo Tools, we can do this very quickly, create a brand new galaxy sample, and then use that to calculate whatever statistic it is you're looking for. So
you're basing everything on the ellipticity of the halo.
So so there's a lot of things you could do. So one option is the electricity of the halo, which defines an axis. You also have the radial information. If you have subhalos, you have the axis of the subhalos. So some combination of these three axes is right now what we're using. You can kind of choose what's the thing you want to align with. But as I'll say at the very end, we're trying to expand this to include more information as well.
Because in your picture originally, you could maybe see that these filaments had something maybe to
Yes, exactly. So let me actually jump to that. So yeah, so this is just a kind of an advertisement. This is fast. So we're actually already running chains, sampling over these different parameters of the model, and it's not, you know, it doesn't happen instantly, but if you put it on a decent sized cluster, you can get a result in a day. And this really is, you know, regenerating a mock every time to do your modeling. So with a little bit more work, I think we can make this usable for actual analyses. But this is exactly what your point was. We're seeing evidence that this halo only information is not good enough. There is larger scale structure that these intrinsic alignments seem to know about. So what you see here is if I just look at the subhalos in a simulation, and I look at the distribution of their misalignment angle with respect to the center of their host halo, you can basically fit this really well with our distribution, and you get a mildly evolving function of the radius within the host halo, where, you know, if you're close in, you're quite aligned. If you go further out, you're a little bit less aligned, but still fairly aligned. We can use this to fit the correlation function. So this is the position shape correlation function between centrals and satellites. And if we use this distribution, you would sort of expect by construction that you get the right answer in the one halo regime. And indeed we do. These different lines are all these different realizations of the model. But in the two halo regime, we're clearly underestimating the correlation. And this is exactly what you're saying.
What is the truth?
So the truth is the blue points with the error bar. So, and this is just subhalos, right? So what this is telling us is that in the two halo regime, the subhalos really do know about their larger scale environments. They are preferentially aligned with other halos in a way that a model that is only based on the one halo information can't possibly know about. And so you might have thought, well, maybe this isn't a big deal, but in fact it is quite observable.
So these are two subhalos in different halos.
This is a subhalo and the center of other halos. Yeah, exactly. And similarly, I mean, you could say, well, what happens if I just want to hit the two halo regime with this model? And you can essentially do it by cranking up the alignment. There's some information still because we're using the actual positions of subhalos to do this calculation. And so there's some memory of the larger scale structure, but when you do that, you completely overpredict what's happening in the one halo regime. So clearly, we need to do better, and we need to somehow include information about the larger scale environment. So this could be a tidal field variable. This could be additional information about a merger history. What's the most recent direction from which a merger occurred, or where is the nearest end neighbors? There's a few different variants that we're considering here. But after we wrap up this paper, which hopefully will be done in the spring, we're going to move on to this and basically say, how can we extend this to include environmental information?
So what mass scale we talk about? Is it galaxy mergers or cluster or filament? What scale is environment factor?
So I don't have a good answer to that other than to say that clearly, so we can go out here now, this is 20 megaparsecs, and even at 20 megaparsecs, we're under predicting the correlations that are there. So whether the mechanism is actually filamentary structure or memory of mergers or large scale tidal impact, this doesn't tell us that, but it does tell us that it is quite a large scale effect. Now it's most noticeable sort of in the 2 to 10 megaparsec regime. So maybe that gives us some hints as to what's going on. But no, I think that's something we want to look at. I don't know what the best way is to solve it.
So as a reference, like, are you comparing to hydro simulations or SAMs? Or?
Are we what, sorry?
Like, are you comparing to hydro simulations?
So this is just the simplest thing we can do. This is just us saying we have a high resolution dark matter only simulation. We can calculate all of these alignment statistics on the subhalos themselves, or we could populate them with our model for what galaxies should be doing. And we're simply seeing that the subhalos themselves know about what's happening on larger scales. So we should do more detailed things we're looking at hydrosims. The problem with hydrosims is you just don't get statistics on these scales. It's actually very hard to do a comparison at 20 megaparsecs. This is a whole separate question, but
This is really the alignment of halos.
this is really dark matter alignments, yeah. But what we're showing is that even that we're not describing adequately with a one halo only model. Yeah. But yeah, the next step would be to go to hydrosims if we could get ones that have large enough box.
But you expect like galaxies to be less aligned and you might get away with.
That's right. That's right. We might get away with it. That's right. But that's not the same thing as saying that the model is correct. But yeah, we might get away with it. So anyway, I'm at the hour. So I'm happy to keep talking. There's been some great questions. But let me just throw up my conclusions. I think that these sorts of combined lensing clustering analyses are very exciting. They're one of, certainly not the only way forward, but they're one of the big ways forward for us in cosmology. We have a couple big projects turning on soon with Rubin and Euclid, and then Roman in the not too distant future. And to adequately use this data and not throw away all this great statistics, I think we need to keep making steps forward in how we're modeling the astrophysics of these galaxies. And I think that will require both analytic and simulation approaches. So thanks.
Questions?
Sorry, maybe I missed this, but so fine. So I understand that the hydro simulation boxes are too small for probing this directly with galaxy shapes. What do we know from hydro simulations about how the galaxies are aligned with their halos? Like that should be an answerable question.
Yeah, it should be, shouldn't it? We know some things. The problem is depending on exactly how you, so take a step back. I mean, the fundamental problem with doing intrinsic alignments with hydro simulations is that you need cosmological volumes, 100 megaparsecs or larger boxes to measure these things. And you need to actually resolve the galaxies quite well because you care about the galaxy shape itself. It's not enough to just know what the baryons are doing in the halo. You really need the galaxy. And this is just a really big dynamic range, which is hard to do. So that's why it's a hard problem. And necessarily when you're trying to solve this, you have to make subgrid assumptions on what's happening on these small scales. And it seems to be, and it's not obvious to me exactly why, but it seems to be that intrinsic elements are very sensitive to these assumptions in a way that a lot of other galaxy properties are not. So you can look across different simulations and ask, are you getting the colors right? Are you getting the stellar masses right? And that seems to be pretty robust. What seems less robust is these intrinsic alignment properties. So there are some trends that we could talk about, but I think we're not yet at a point where we could look at a hydrosim and say this is definitely how galaxies and halos are aligning. This seems to be particularly true for spiral galaxies. It's more consistent with sort of blobby red ellipticals. There's some, as you kind of expect, just correlation between the halo axis and the major axis of the elliptical. The exact degree of that depends on the hydrosim. What's much less clear is what happens with spirals. There seems to be some mass threshold where it flips from being aligned to anti-aligned based on some spin property. But where that occurs, and indeed whether it occurs, seems to be much more sensitive to the hydro assumptions. Yeah.
So what's the redshift range of your redshift bins?
For DES?
Yeah.
Gosh,
Roughly.
I'll have to look this up. I actually don't remember. I mean, we're talking about redshift about 1.2 or 1 for the highest redshift.
And down to
0.2.
Okay, I just wonder, I mean, you have the weak lensing, I mean, you have the clustering of the galaxy, which is the delta matter there, but then the weak lensing is some kind of integral along the line of sight.
Yeah.
But still, so when you combine them, and you do each redshift bin separately, or when you combine them and all the whole redshift.
Yeah, it's a joint forward. Model. Yeah, exactly. So it's a joint forward model where you have some parameters that are talking about the full matter distribution across all the redshift rings. Then you have some parameters that are redshift dependent, sort of, this redshift bias, this bin's bias, this bin's intrinsic alignment. But you have a single model that incorporates all these parameters and jointly fits all the cross correlations.
But you also have the part at low redshift, which only affects the lensing, which I guess reduces the correlation somewhat.
Part at low redshift.
Below the lowest redshift bin, or that's not.
I mean, there's not much volume there. This is a detail. We looked at this a lot actually because we tried 2 different photometric redshift methods, and it actually there at exactly what we did at the low redshift end actually seemed to make a difference. And I can't even remember now what the conclusion was, but that there isn't enough volume down there cosmologically to make a difference.
So it's related to, so you're saying that, so the galaxy and intrinsic, also the intrinsic alignments only happen locally, but the galaxy is again an integral, but still there's a significant enough correlation.
It happens locally with the mass, which then lenses background galaxies. That's where the correlation comes. So if you have two galaxies close to each other, then locally they can be aligned with each other.
Right.
But if you have a galaxy here, it's locally aligned to this mass, and then this mass is also lensing this galaxy back here. So when I correlate these two galaxies, this is where this cross term comes from.
The galaxy is different redshift.
Exactly. So I guess this is your point. If it was just this effect, you would just say never correlate two galaxies that you think are in the same redshift region, but that's not enough. Yeah.
More questions? Any questions from Zoom? If not, then let's thank Jonathan again.